Hello, welcome back to Slow-Mo's YouTube channel. So what we're going over now is space science. Basically what I did with these notes is I put together a bunch of space stuff, all the random, interesting, fascinating space science stuff that you guys always ask me questions about, and the stuff that you need to know. And it's not really in any particular order or anything like that. It's just a bunch of things that I wanted to teach you. So let's go ahead and dive right into it. The universe. The universe is everything that exists. Here you have a picture that was taken by the Hubble telescope, and it is just one tiny fraction of what's out there. And so a lot of the time when you actually look out into the sky and you see what you think are stars, they're actually not stars. They're entire galaxies out there. So we have a universe that's made up of billions and billions of galaxies, and each one of those galaxies is made up of billions and billions of stars. So I think it's pretty selfish of us to think that we are the only life that is out there, that exists, because there are plenty of other stars that maybe have planets that are in that habitable zone that could actually be supporting life. That's just kind of what I wanted to say about the universe. Don't forget that everything that I have in red is what you need to fill in into those blanks on your notes. The Big Bang Theory. This is really, really important that you understand this. So this is the theory of how the universe was formed. Although we're using the word theory, remember in science, when we use the word theory, it's got a lot of facts behind it. It's got a lot of backup behind it. It's got a lot of research behind it and evidence behind it. And so what happened, or how the universe was created, is it all started out as one big ball of matter, which actually was kind of small, but it included everything. All the matter that exists was in this one small point, and it exploded. And it's actually still exploding today. So if you look at the picture here, it shows little galaxies, and a lot of people said that these look like infinity stones. They're not infinity stones, but they're galaxies, and it's trying to show you here that they're actually still spreading apart. So we can actually use instruments to measure how galaxies are moving or where they're at, and we can tell that they're actually still separating from each other, and they're moving away from this center point where everything started. So if we imagine, like, hit and rewind, right, and everything goes backwards, kind of like what we talked about with Pangea, we can tell that everything started at this one central point, and everything exploded from there. So that's the Big Bang Theory. Now, what's going to happen in the future? Well, there's two ideas about what could happen. There's the open universe theory, which states that everything just keeps spreading forever and ever until all the stars burn out. Or there's also the closed universe theory, which states that after a while, things are going to expand to a point, and then they can't expand anymore. Basically, the gravity at the center of the universe is actually going to pull everything back together, and there's going to be a big crunch. And then maybe it's a cyclical thing, right? Maybe it's going to happen again. Maybe there's going to be another big bang and then another big crunch, and so on. A galaxy is a gathering of stars and gas and dust, and it's actually being held together at the center by a black hole. And so a black hole is actually not a hole at all. There's a slide about this at the very end, but I'm going to go ahead and talk about it now because it's what holds the galaxy together. So a black hole is actually a big ball of matter, and it's so dense and so massive that it has a crazy amount of gravity, so much gravity that it can hold all of these stars together. And it makes these three different shapes, which I talk about in the next few slides. So a spiral galaxy has arms around it, and the Milky Way is an example of a spiral galaxy, which is the galaxy that we live in. And they thought that it looked kind of like spilled milk when you would look out into the sky, because basically we're in the middle of this flat galaxy, right? It's like a plate. It's like, imagine being inside of a plate and you look out, you can see the edge of the plate around you, and they thought it looked like spilled milk, so they called it the Milky Way. And so spiral galaxies are actually the older, kind of more mature galaxies, and these have been pretty much fully organized into spirals. Here's a picture of our Milky Way, looking at it from the inside. Elliptical galaxies are not as organized, a little younger than spiral galaxies, and they're basically either circles or ovals. And irregular galaxies are just kind of like blah. They're not organized at all. They're pretty young galaxies that are barely forming, and they have funny shapes. They don't have any kind of shape to them. They're just kind of just like all a mess. The sun is at the center of our solar system, of course, and it's what keeps everything in our solar system in place, revolving around it. It's perfectly spherical, and it is made up of mostly hydrogen and helium. We'll talk about this a little bit more when we do the solar system notes, but you should know that the sun is very average. In terms of temperature, it's average, it's in the middle. In terms of age, it's in the middle. In terms of brightness and stuff, it's all in the middle. It's just a very average star, which makes it really nice for a planet that has life, right? Remember, when we are looking for life in other solar systems or other galaxies, we need to find a star that is going to make a nice environment, on a planet. If we have a star that's a little hotter or brighter, we would want to look for a planet that's a little further away, right? We want liquid water. If we're too close to a star, it could make all the water evaporate. If we're too far away, everything would be ice, and so that doesn't make it very conducive to life. And so our star being really average kind of makes it a little easy that way. But if there is another star out there that's got planets around it, right, we need to kind of look inside of that habitable zone for that star. How far away would we have to be from that star in order to maybe find life there? Meteors are moving objects, and they are mostly moving in a straight line. Sometimes they get pulled by gravity and they get pulled in to hit something or just moved a little. But these are not asteroids, right? Asteroids are going around the solar system, right, in the asteroid belt. So I've got a couple of examples of meteors in the class, and so we can take a look at those later. Here's a picture of Meteor Crater in Arizona, and I just wanted to show you some examples of what a meteor crater looks like. Now, this is nothing compared to the size that killed off the dinosaurs, but here's their website. You can actually go visit it. And so this, if you look at the top over here, that's actually the parking lot of the visitor center, which is kind of crazy. That's the parking lot, and then you see like cars and stuff, just a couple of cars there in the building and things. And this is the meteor. And so I've got a little some information here about how big it is. 4,000 feet in diameter. That means across it's 4,000 feet, 570 feet deep. And here's a picture of a guy next to it. You can't actually go inside of it. Only scientists are allowed there, but you can walk up to the edge and look inside of it. The bottom picture here, you can see the visitor center again. And this is a piece of that meteor, that caused this crater. And you'll see that it's 54 yards across, like the actual one, the whole thing was 54 yards across. So we're talking a little bit over half of a football field. That's how big this meteor was. But it is still nothing compared to what killed off the dinosaurs. So the impact theory is one of the ideas, right? One of the reasons why dinosaurs died off. And it was this plus this huge chain of volcanic eruptions that happened in India, and basically kind of like a perfect storm of things happening at the same time that actually caused the demise of the dinosaurs. And so when the meteor hit, it kicked up a lot of dust and debris into the atmosphere, blocked out the sun, stopped photosynthesis. All of the volcanoes erupting, they released a lot of carbon dioxide and other gases, and it caused a major greenhouse effect. And so that was another reason why a bunch of the big reptiles died. But that allowed for other organisms like early mammals to actually evolve and eventually turn into us. So here's the Chicxulub crater in the Yucatan Peninsula near Mexico, or really kind of right on Mexico. And this is where the meteor actually impacted. If you were to compare the meteor crater in Arizona to this, it would be like one little pixel on this picture. So an asteroid is part of the asteroid belt that orbits around the sun. A comet is basically a dirty snowball. It is ice and dust that travels around in a really crazy orbit around the sun. The reason I say crazy is because it's not like, you know, the planet orbits, it goes around kind of in a sort of circle. This is like a really elliptical orbit, so an oval. And so sometimes it gets closer to the sun, and when it gets closer to the sun, it melts a little bit, and we've got this tail that forms. A satellite is going to be anything that revolves around something else. So a lot of them are man-made, for example, like the satellites that give you your cell phone service. But then we also have one natural satellite for Earth, which is our moon. A nebula, I think nebulas are like the most prettiest thing ever. A nebula is basically like the birthplace of a star. It's like a star nursery. So these will eventually become stars, and they're basically clouds of dust and gas. A light year, this is also super duper important. Light years are actually a measurement of distance, not time. A lot of people think time because it has the word year in it, but it's actually a measurement of distance. So if you think about it, the sunlight that leaves the sun left, and it, like, let's say it's, you know, coming towards you and it gives you a sunburn, or it touches your skin and you can feel the heat from the sun. That heat, that light actually left the sun 7 minutes ago. So that's how far we are from the sun. It takes 7 minutes for that light to reach us. And so stuff takes time to travel, right? And so if we imagine if that light were to travel for a whole year, it leaves the sun and keeps traveling past Earth, and it keeps going on and on and on, where would it be after a year? Okay, that point that it reaches, that's a light year. So that distance that light can travel in 1 year. So in space, we're not going to use miles or kilometers, because we would end up with these crazy large numbers, right? It would be like me using millimeters to measure the length of my classroom. I would end up with this huge number that would be too hard to deal with. So in space, we use light years for distances, because then our numbers will be smaller and it'll be a lot easier for us. And so a light year is how far light travels in 1 year. A black hole, like I mentioned before, is basically a big ball of matter that has a lot of gravity. It's very, very dense, so it's going to have a huge gravitational pull. And it's so strong that not even light can escape it. And so we are actually being pulled in by the black hole, but don't worry about it. It's not going to pull us in for, another long time, millions and millions of years. But that's basically what's keeping us in orbit, the sun, the whole solar system in orbit around this black hole in the galaxy. Okay. Thanks for listening to the Notes About Space. Make sure that you check out the other videos.